In this video, I'm going to go through Unit 5 of Edexcel Physics, the Astrophysics part of it, the Astrophysics ISP. I'm going to go through Task 1. So the main things covered in this task are gravitational electric fields and comparing and contrasting them, luminosity and black body radiation, and the life cycle of stars. So let's go straight to explaining everything tasks, which I've just gone straight past. Here we go. Okay, so compare and contrast gravitational fields, include equations, diagrams and definitions. Right, now, if I remember correctly, there's a brilliant website that goes through this. So I'll just bring that up so we can have a look. It's called s-cool. So if I do s-cool, gravitational and electric fields. Here we go. It's first link there. Spelled gravitational wrong, never mind. Okay, so here we go. Literally a direct comparison between the two in terms of equations. So in terms of the Edexcel course, all of these need to be required apart from this idea over here. These ideas in terms of the equations over here aren't required. Everything else pretty much is, and it goes through it very well. Okay, so feel free to search the way that I did and have a read of that for that one there. There's no point me sitting here and talking my way through that. It's pretty self-explanatory and it goes through it very well and in good detail. Right. Next, compare and contrast the life cycle of a large star with a sun-sized star, include information about the processes within a star. Okay, so the main processes that we're talking inside of the star are nuclear fusion, okay, and gravity pulling everything together. So gravity is a force acting inwards, okay, nuclear fusion is a force acting out. So gravity pulls everything in, okay, and you have radiation pressure or nuclear fusion pushing out. So remember, in the life cycle of a main sequence, in the main sequence of the life cycle of a star, those two forces are equal. Okay, so during the main sequence, those two forces are equal. Remember, the life cycle of a star follows two different paths. Again, there's no point me trying to draw something out where we've got very good pictures of it on the internet. The life cycle of a star. Okay, so this is the absolute basics of what happens. Everything, remember, starts. Let's make this bigger. We'll zoom in on that as well. So everything, remember, starts from the idea of a nebula. So a nebula, is, let's just make this webcam smaller, there we go. A nebula, remember, is just dust and gas that's there in space. If it's of a low enough mass, it will end up becoming an average star. When gravity pulls everything together, things move fast, high temperatures, high pressures. Essentially, we start nuclear fusion, as a star begins. If it's a larger mass, it ends up becoming a more massive star. In each of these steps, as it goes from one to another, there's a change in terms of what's being fused. Okay, that's the basics of what's actually been happened. So originally, hydrogen has been fused to helium, but when the hydrogen runs out, the helium needs to be fused, and that essentially causes a greater amount of energy to be released, and therefore the star changes size. That's what's happening in each of these stages. When you end up with a red giant, go from a planetary nebula. This planetary nebula is just what's ejected from the outside of this star. Okay, it does do this a few times in terms of going from a red supergiant. It sort of oscillates and gets smaller again, oscillates and gets smaller again. This planetary nebula that's sort of left behind, that then can go on to make new stars and new planets. Okay, but eventually this ends up being a white dwarf. The more massive star, because of the fact it's got a larger mass, that means it'll be a larger force of gravity pulling everything together, and therefore will fuse these heavier elements that are ejected in terms of supernova. So this final expansion that takes place, it's going to fuse heavier elements and therefore release larger amounts of energy, and therefore essentially explode. So what could be left from that as a neutron star or a black hole? That's pretty straightforward. Okay, so the book goes through that very well as well, in case you want to use that. Let's just make this a bit smaller. There we go. Right, so let's get stuck into these questions. So first one over here. Gravitational field on the Earth is g, the gravitational field on the surface of the planet is of twice the radius. Okay, so the radius is going to be twice the amount. Okay, and the same density, so density is going to be the same, it's going to be twice as big, so r, so remember g is related to r, so it's related to 1 over r, let's just, no, sorry, g is, let's get the equation up and I'll show you what I mean. I've gone the wrong way, yeah, I knew I had. Right, I haven't got the equation this one here. Did have it a minute ago on here. I'll show you what I mean. No. Okay, well let's just go through it. It's going to end up being twice the 2 times g. Okay, the reason why is this: even though the radius has gone down, so even though the radius, so okay, let's actually write out the equation. It's going to be, I think I saw it here actually. Yep, there it is. Okay, so even though the radius has gone down, so therefore we think, okay, if this is going down, then this is going to get like much bigger because of the square relationship. It's not as straightforward as that. The idea is that mass is equal to density times volume, so therefore the radius is going to affect the mass as well. So what you actually end up with is density times 4 over 3 pi r cubed. Okay, so if I put that into there, okay, I can start cancelling out my r's, so that ends up just being r. That's just gone entirely, so that ends up being r. So you can see that density, so gravitational field strength and r are directly proportional. So if I doubled the radius, it's the same density, I've doubled my gravitational field strength. Okay, so that's why it's b. I'm sorry about the long-winded way of going about that. I was trying to do it without going into that, but to be quite honest, that probably is the easiest way of doing it. Okay, the equation, I equals L, so intensity is equal to luminosity, divided by 4 pi d squared, where d is distance, and L is luminosity and I is intensity. Yep. So use this equation to show the base units of intensity are kilogram seconds cubed. Okay, so let's go through each of these and know what they actually are. So your idea that we've got to use is we're going to know that watts is equal to joules per second. Joules is equal to Newton meters. Therefore, watt is equal to Newton meters per second, and a Newton is equal to kilogram meters per second squared. So watt is going to be equal to kilogram meter per second squared meters seconds to the minus 1. So what we end up with from that, if we cancel, is kilogram meters squared seconds to the minus 3. But we've only done the top line of the equation, so we've only done what luminosity is. Now we need to divide by this d squared. So that's what a watt is. So that's L from before. So we want L over 4 pi d squared. So that's going to end up being that divided by, sorry, this over here is a 2, you can't see it very clearly, divided by meters squared. So those cancel out and you're left with what they want. Nice 3-mark question, very nice 3-mark question. Calculate luminosity of a star with intensity 1370 and the distance of 1.49 times 10 to the 11. Okay, so it's pretty straightforward. All you need to do is to rearrange the equation. So you end up with L is equal to I times by 4 pi d squared, and then sub in your values, and then what you should end up with is about 3.8 times 10 to the 26. Right, next one. Explain the difference between luminosity and intensity of a star. Remember, luminosity is the power, or joules per second essentially, while intensity is the power per unit area, okay, or power per meter squared. Okay, so luminosity is measured at the star, and intensity is measured at a distance from the star, or an observed distance from the star. There you go. Okay, so there are your 3 marks that really come from that. So 1 from defining luminosity, which is the same as power, or joules per second. 1 from defining intensity, so that's power per unit area, or power per meter squared. And a 3rd mark is from essentially stating that luminosity is measured at the star, or intensity is measured at, and intensity is measured at Earth. Okay, so either one of those 2 last statements will get it for you. You could state the equation, and that will get you the 3rd mark as well. So stating the equation we've just been through in question 9. 10bi. The sun has a surface temperature of 5000 Kelvin. Calculate the intensity of the spectrum as maximum. Okay, so essentially we're using Wien's law. Okay, and essentially just stepping straight into Wien's law. Wien's law is a standard equation. It's very straightforward. It is given to you. So I'll show you which one that is. It's just this one here. Very straightforward. Okay, so it's just subbing straight into that. So you're doing the constant that's here divided by temperature. That tells you the wavelength. Okay, so nice question to get on that. The problem is that the majority of students will get that one. The radius of the sun is given to us there. Show that its surface area is approximately equal to 6 times 10 to the 18. So we've been given the radius, and we're trying to figure out the surface area. Okay, so to figure out the surface area from radius, if you didn't notice already, it's just 4 pi r squared. Okay. Hence, calculate the luminosity of the sun. So 4 pi r squared, by the way, gives us surface area, in case you didn't catch what I just said there. So now we need to figure out the luminosity of the sun. So the equation we're using for this one is another one of the luminosity equations. So it's L equals sigma A t to the 4. Okay, so that's where you should know this from. You should know that the surface area is equal to this because we've used it as part of this equation here. We've substituted it in for that before. If you do that, you should end up with a value of about 4 times 10 to the 26, or 3.9 times 10 to the 26. Let me just show you where that equation is. It's over here. So you can see they've subbed in that for area. So they've subbed in 4 pi r squared for area. Right, 11. So we've got the idea of a filament lamp, okay, and we've got a log graph for it, so log power against t. So we need to use the graph term in n. It's straightforward. You just need to find the gradient. The gradient of that graph is going to give us the value of n. Pretty straightforward. Should be able to do that. A student comments that this relationship is predicted by Stefan-Boltzmann law. Comment on the statement. Well, it needs n to be 4. Okay, so if the gradient of that graph was 4, then it is predicted by the Stefan-Boltzmann law, because that's how power is related to luminosity in the Stefan-Boltzmann law. Okay, so if the value of n was about 4, then we're about spot on. So I won't check that, but you guys can check that if you want to. Or you should check that as you do the question. Right, planet of mass m orbits a star of mass m, so little m, big M. The radius of the orbit is r. By considering the force required for circular motion in this situation, show that the time period of the orbit can be given by, right, so we've got part that's missing here, but you should know this. It's a common, how am I going to do this? Let's put enter over here. That will allow me to figure it out. There you go. The time period of the orbit is shown by t squared is equal to 4 pi squared r cubed over gm. Okay, so this is a standard derivation. Okay, so the idea is we need to consider force. So if we're considering force, we know it's circular motion, or we assume it to be circular motion. So it's be F is equal to mv squared over r. Okay, and then we know that the F in this situation is caused by gravity, so it's G big M little m over r squared. Big M little m over r squared. Well, we know that V is equal to 2 pi r over t. So V squared is equal to 4 pi squared r squared over t squared. So we need to put that into there. So F is equal to m 4 pi squared r squared over t. And we've still got to do this divide by r, so it's multiplied by 1 over r. Okay, so that 1 over r is going to cancel with one of the r's there. That's straightforward. I've got nothing else to cancel out there. So you end up with 4 pi squared m over t is equal to g big M little m over r squared. M's cancel. And then it's a straightforward rearrangement from there. I seem to have lost an R somewhere. Oh yes, that R should have ended up on top rather than cancelling. There you go. That ends up being R cubed there. So when you bring this over, it ends up being R cubed. Sorry, that was an R squared. I've written this bit over here wrong because it's divided by R. Because you've got a divided by, it flips over and comes up on the top. So it should have been multiplied by R over 1. Sorry, so end up with R cubed. There's my mistake over there. So you end up with R cubed on top. So I still had an R, should still have an R there. Hold on, I seem to... No, I think I did it right. R squared. So I'd R squared, let me go through this again, sorry. I'd R squared cancelling out by R, so that gave me just R. Yeah, I forgot to take my, I had an R there. I did this the right way around originally. Why am I being so silly? So what ends up over here, that was me R squared, cancel it out, so I end up with R. That's what I forgot there. So I had my R here that I forgot. So let me just go through the last part of that again. So I substitute in that into here. So I end up with F is equal to M 4 pi squared R squared over T squared. Yeah, so I missed out my t squared there as well, I just saw that. And then we've got to do that, multiply that by the 1 over r, because we're divided by r, so the same as multiplying by 1 over r. Okay, so the r cancels out with the r squared there. Now we need to set that equal to your f from before, your f for gravitational field. So m, there we go, that's the r that I forgot, over t squared is equal to g big M little m over r squared. Okay, the little m's cancel, rearrange for t, and bring the r squared up, so end up with t squared is equal to, bring the r squared up here, so it's 4 pi squared r cubed over gm, which is exactly what they wanted. Yep. Okay, so sorry about the small mistake I made there. Just to show the last few steps. Play that back if you need to. So the mistake I made was not which I just missed out my R as I went through it. But a nice 3-mark question to get. So, measurements have been shown that a planet which orbits a star with a period of about 6 years, the radius of the orbit is 3 times the radius of the Earth orbit around the Sun. Use the formula A to determine the value of the ratio of the mass of the star to the mass of the Sun. Okay, so now we can remove all the constants. Okay, so all the constants in this equation are G for pi squared. There we go. So all we've got is r cubed over m, really. The radius of the orbit is 3 times more. And we want to know the ratio of the masses now. So essentially you end up with a situation that mass times the time period squared, because everything else cancels. If you had mass times time period squared over r cubed, so this is the next question now, remember, this is not the same as a bit before, this is II now. That's a constant, that's a constant, that's a constant, so they can go. So the idea is t squared multiplied by m divided by r cubed must be a constant. So you can set that equal to each situation. So that could be before, so of the star, and you could have the same situation for the Sun. So if you compare those two values by plugging in the numbers that have been given, so you can see that the star has a period of 6 years, while the Sun has a period of a year. And if you put in all your values, you end up with 27 over 33 for your. So the star ends up being 27, and the Sun ends up being 30. Let me just put it from calculator. 36. Okay. So your ratio will therefore be 27 to 36. Okay, so they're the values that you actually end up with for your ratio. Okay, so that's the idea you use. You got to multiply a mass. You can just set any mass. You can set it, you've got to figure out the mass of the. Let me take it a step further to make it a bit easier. I feel like I'm waffling. It's a morning in the holidays. You'll have to excuse me. All right. So we have this idea here. That's at the start. Mass of the Sun. Okay, so that's of the star and that's of the Sun. So we want m star over m Sun. So therefore, that's going to be equal to the time period, the radius of the star over the time period squared of the star, the radius, so time period squared of the Sun over the radius of the radius cubed of the Sun. Okay, so that's what we actually end up with from that. So you can't see that under there, but I'll show you from here. If you rearrange this to have the mass of the star over the mass of the Sun, that will give you the ratio that you want. So rearrange this for that and then figure out each of the values. So this value here will give you one of the values, and that value there will give you the other one of the values. Okay, and then these are blank. Okay, so you've got a ratio there. Okay, so figure out what that value is, and then one over the other will give you the value that you want. Brilliant. With one over the other, we'll get the value of the ratio. Because of the presence of a planet around HD 70642, doesn't remain at rest. Instead, the planet and the star both wobble around a common centre. Explain why the orbiting speed of the star is very small in comparison to the speed of the planet. Right, okay, so we've got the idea of one object orbiting another. Okay, so the larger planets will move around the centre of mass. So the larger planet and it is a planet. Yeah. So the larger planet and this smaller star. Well, the larger planet and the star. I didn't say it's a large planet actually. This planet and this. I'm just assuming it's a large planet because it's making the speed is varying essentially. So this planet and the star will orbit this common centre of mass. So they'll both have the same time period around the centre of mass. So the star will go through a smaller distance, and therefore it must be going faster to do that. So you have the same time period around a common centre of mass, and therefore the star's going a smaller distance. So it's small compared to the speed of the planet. If it's going a smaller distance, it's going slower compared to the speed of the planet because the time period is the same. Astronomers discovered the planet by observing the Doppler wobble effect. As the planet orbits a star, the light from the star undergoes a Doppler shift of frequency. Explain why this method will only detect very large planets. Remember, the Doppler shift needs to have a large change of... the Doppler shift only is really visible when there's large velocity is taking place. Okay, so only if there's fast movement will this take place. Okay, so the larger planet will move towards centre. The larger planets will move towards. Will move the idea of the centre of mass towards the planet, so it moves it away from the star. This makes the star move faster. Okay, so therefore the Doppler shift is going to be greater at larger speeds, which means it's more likely to be detectable. Okay, 13a. So in 13a we've got Newton's law for gravitational force between two planets. Okay, so that's F is equal to G M, big M, little m over r squared. So F is equal to G, big M, little m over r squared. I need to define G and the m's and the r. Okay, that's essentially going through Newton's law of gravitational forces. Okay, so we need to use a graph to demonstrate the relationship between G and the distance from the centre of the Earth and show that it obeys an inverse square law. Okay, so you need to take any sort of two values off the graph, okay, and show that if you doubled the distance you are away, you've actually quartered the size of G. Okay, so any two values, and if you double the distance you are away, you've quartered the size of G. That's the idea you need to sort of really be looking at. Or if you treble the distance away, then you've ninth the value of G. So you've got to actually check that it's an inverse square. Pretty straightforward. The average distance between the centre of the Moon and the centre of Earth is 380 megameters. That is nice to put a megameter in there. Use the information from the graph to determine the Earth's gravitational field strength at this distance. Okay, so you need to sort of extrapolate the graph. Have they got that value on there? Oh, they've got it on there. Okay, so you could take a value pretty much straight off the graph for that one. Okay, and you should get somewhere in the region of about 0.0027 or 0.0031. What effect, if any, does it have on the Earth? Okay, so it means does it have on the Moon? Okay, so the Moon maintains its orbit around the Earth. The Earth, that gravitational force, is what is keeping the Moon in orbit. Okay, and it rotating around the Earth. Okay, so that is providing a centripetal force. So therefore, this keeps it in circular motion. Any of those ideas will get that mark. Right, 14. A student says that once you know about electric fields, you can apply the same laws to gravitational fields. Write a set of revision notes on these two types of field, stating the similarities and differences between them. So we've already done that in the explaining everything task, so we don't need to really do much more about it. But feel free to look through the mark scheme on it. Okay, it goes through it very well. So remember, they're both inverse square laws, or you can quote the equations if you wanted to. Both are radial, and both fields have an infinite range. But they approach zero when you're really, really far away from the source. However, electric forces are attractive and repulsive, but gravitational are not. Electric forces are much stronger than gravitational forces. Then electric forces only act on charged particles, but gravitational act on everything. Electric forces can be shielded. It's the idea of Faraday's cage, which some cinemas have, and those sort of ideas, but gravitational forces cannot be shielded. Okay, so 15. Experimental diagram. So we've got a little bit here on the life cycle of a star. The x-axis is log t. Okay, so the reason why we use logs is because if you have a large range of values, it's easier to plot. So it's the answer to this is A, because the range of temperatures on the surface of stars is large. Okay, so it's easy to plot a large lot of values on a log graph. Okay, so that finishes ISP task 1 on astrophysics. I apologise for me stumbling my way through the middle part of it, but hopefully you still found it useful. Thank you very much for listening.